The last interesting speed in the Maxwell-Boltzmann distribution for gas particles at P, V, and T, all treated as constants, and that is called the root mean squared velocity. And the way we get that is, interestingly enough, looking at the pressure for the hold on, my pen's freaking out. Okay, cool. By looking at the pressure on the walls of this model over here. So assuming we drop a particle in here with a certain momentum, and we let the x direction be A, and actually an easier thing to do is let's just restrict the movement in A, and we'll say that, yeah, obviously this is the z direction, and this will be the y direction. We'll just say that z and y can be anything. So we have like a function, and y can be anything. It doesn't matter. Z can be anything. And this is an a in here. So x can vary from 0 to a, and z and y are irrelevant. And we wanted to take a look at the momentum of this particle. We would say it's equal to mass times velocity in the x direction, and this is the mass of the particle. And this is for the model in which the particle goes a distance a. So delta x over this situation is just going to be a. And the distance, where's my cursor? Okay. So looking at distance equals rate times time for the situation of going from this wall to this wall. The change in the distance is equal to rate times, yeah, the rate's going to be the same. So that here we have a is equal to Vx times delta t. And in this case, since we're starting from time equals 0, the f of b minus the f of a in this situation is just always going to be what the f of b is. So we can go ahead and say that a length over the velocity in the x direction will give us the time between, well, basically the time to go at distance a with speed vx, and the force in this situation, which is mass times acceleration, which we write as d dt of v. We'll write m. The acceleration is v times t. I mean, what am I? Sorry. the so the velocity is a constant. That's Vx, and the change in time is A over Vx, but we can just write this in terms of the momentum for right now, because mass times velocity is momentum. And let's consider the pressure now that we have the force. So pressure is equal to force over area. We have the force, which is momentum over time, times 1 over A. A is the plane that is created with y value and z value, which are constant. So considering that delta t is equal to A over Vx, we would have P over Yz times A over Vx, and using this form again for momentum, mvx squared over this value and this value and this value is the volume. And yeah, so this would be a model for the pressure, the force, and obviously the position given a particular delta t and delta x. All right, so we came up with an expression for the pressure, which was mvx squared over the y. Hold on, my pen is being weird. Yz times the length a, which is also mvx squared over the volume. So that leads us to our ideal gas laws when we multiply the volume over to the other side. However, this is just for the x direction. So what I meant by that is we can replace this with an nRT or an nk, capital NKT. So let's think about how we can convert this into a 3D representation, recalling that V total squared is equal to Vx squared plus Vy squared and Vz squared. So how are these two guys related? Assuming that these three are all the same, they're 1/3 of the total value. So we could say that 1/3 v is equal to vx. And then we could replace what we need in this formula over here. So we would have an nRT from the ideal gas law replacement on the left-hand side. On the right-hand side, we would have an m v total for three-dimensional. So what we want to say here is this used to be vx squared, and we want it to be v except a third of v. So this needs to be squared, and this needs to just be divided by a 3 afterwards. Yeah. And yeah, this is total. And we've got the volume on the other side. Yeah, that's everything we need, I guess. And so we could say that v is equal to, v squared is equal to, oh, I'm sorry, we forgot this guy. Oh, no, we've got that over here. But we did forget to put an n here for the 3D representation, and for sorry, the 3D representation didn't have to do anything with it. That just meant we could use one particle in a three-dimensional sense. We did have to also put this factor of n inside here because now we're talking about any number of particles. So we can see that this cancels here, this cancels over here, and v squared is 3 Rydberg's constant times t over m. And when we take the square root, we can see that the root mean squared velocity is 3RT over m. And this is the form you usually see it in most physics books.